Welcome. We're now going to move into Module 3, which discusses catalysts and membranes. And this topic covers some concepts that you'll find in Chapter 5, but these should be a review. And then we're going to focus on Chapter 6, covering enzymes as biological catalysts. First, you should be familiar with the first and second laws of thermodynamics, stating that energy is always conserved, and in the second law, that the world tends towards disorder or entropy. From the second law, we can think about Gibbs free energy, delta G, and how we can calculate Gibbs free energy from the change in both enthalpy, which is delta H, and entropy, delta S. With Gibbs free energy, you want to pay attention to the sign, because here, a negative delta G, that is considered an exergonic or a spontaneous reaction. For a positive delta G, shown in red, those are our endergonic or non-spontaneous reactions. However, just because a reaction is favorable, it doesn't mean that it'll occur in a time frame that the cell needs it to occur in. This is where enzymes come in. Enzymes can speed up reactions by lowering the barrier for energy, or the activation energy, E sub A, and that's shown here on the graph. And that is because of the transition state, the high point in our free energy. And so enzymes that catalyze reaction will lower the activation energy of our transition state and increase the rate of a reaction. Enzymes are catalysts, and they work again by lowering that activation energy through a reversible and transient complex with a substrate that stabilize the transition state. And again, they only change the rate of a reaction. You can see here the delta G is the same before and after the addition of that enzyme. So they're not changing whether a reaction will occur at the position of the equilibrium, they just change the speed. Enzymes are generally proteins, and so like proteins, they have an optimal temperature range and an optimal pH range, and it varies depending on the enzyme. And enzymes work by stabilizing the transition state of a substrate in the active site of that enzyme via some non-covalent interactions. They can do things like distort bonds, transfer protons or electrons, and activate the substrate that way. Based on this, what kind of amino acids do you think you'll most likely find in the active site of a protein enzyme? Try to think through that for a minute. Next, let's talk quickly about some enzyme kinetics. We assume here that enzymes follow Michaelis-Menten kinetics, where you can plot the change in substrate concentration on the x and the initial velocity of the reaction on the y. And this equation is going to give you a Vmax, which is the saturation. Try to think through why that occurs. Why do we reach saturation when we're talking about enzyme kinetics? Why is there a point where no matter how much more substrate we add, we cannot make the reaction go any faster? From the Michaelis-Menten equation, we can also get Km, the Michaelis constant here, which is equal to half of the Vmax. So it's the substrate concentration for half the Vmax. And we get this equation here for calculating Michaelis-Menten kinetics with the velocity equal to the Vmax times a concentration of a substrate over that constant plus the concentration of the substrate. And you'll be given the Km that is given for a combination of an enzyme and a substrate. Graphically, Km again is shown by that half Vmax. And if you look at the slope here, that change in initial velocity, this is the point where that is the most linear. Finally, we can regulate enzymes in a few different ways, but I'm going to talk about allosteric regulation. An allosteric site is a site that's not the active site of the enzyme. So shown here is a RC combination, and we have an active site on C and a secondary site on R. That's our allosteric site. Allosteric inhibitors or activators will bind to that allosteric site and change the conformation of the active site of the protein. So shown here, when you bind the allosteric inhibitor to site R, you change the active site in C. So it goes from a large triangle to a smaller triangle, blocking the addition of substrate. so inhibiting or turning off that enzyme. In the same way, you can have an activator bind to an allosteric site and allow for substrates to bind. In this video, we reviewed the first two laws of thermodynamics, and we talked about how enzymes act as biological catalysts. Next time, we're going to talk about the plasma membrane.